Hey, hi there. Welcome to this session on SystemVerilog packages and pre-processing. So, as a part of this session, we will look at how can you package your SystemVerilog code for delivering and for further reusability within the project. What are some of the mechanisms that are available? Let's look at it. Let's quickly jump into the agenda. So, we will first start off with the set of compiler directives. We have been using them already. For example, we have been using tick time scale. We have been using tick include. At some places we have used tick ifdef, but we have not discussed them. So let's discuss them as a part of this session, and then we'll be looking at packages, SystemVerilog packages, how we can use that to package our code. And then there are a bunch of utility system tasks and functions. Those also, few of them we have been already using. So we'll quickly look at the categorical level. We'll not go into the details of every function, but we'll categorically mark what is available, and then we'll very quickly look at last three topics as to what is a program block, checker block, and then we will briefly understand what is DPI. So the scope for learning compiler directives is we will look into tick include, and then we'll look at the tick define, and then we will look at tick ifdef, tick else if, tick else, and tick end if. There is one more flavor, tick if ndef, right? That just the negates. There's not a fundamental concept. It's derived based on this, and then we'll close it up with the tick time scale. So what is a compiler directive? Let's ask ourselves that question first. So these are also, known as a preprocessor commands in C. Some of you, if you have done C programming, you would have seen that they actually have the origination from that. From there, they have come into the SystemVerilog. SystemVerilog, as you know, is sort of in a way influenced by many languages. So this aspect, it's influenced from the C. And since when we say it's a pre-processing stage, right? So still the SystemVerilog compiler has not kicked in yet. So what happens is you have a source code, and then there is a step called pre-processing that takes place, and only after the pre-processing step has completed is when the actual analysis of the SystemVerilog constructs and the compile process for them starts off. So what we are going to talk as a compiler directives actually get processed in this particular stage. So at this stage, the awareness to the SystemVerilog constructs is not there. Okay, so that is what happens over here. So the compiler directives are preceded with this tick character. It's on the top right corner of your keyboard, just below the escape key. You should be able to see it. This character is called as like a grave ascent. Its ASCII code is hex 60. Why I'm sharing this information is sometimes when we look at these symbols, there is very slight difference. So just to help you distinguish, I'm calling this information out, and it is different from this character which is apostrophe, and this character is near the enter key. So just on the left hand side of enter key, you will see this apostrophe character, and this character, this is not what we use with the pre-processing directives. The one that we use is, as we talked about, that's one on the top left corner just below the escape key, right? So and slightly orients towards the left. And the scope of compiler directive extends from the point where it is processed across all the files processed in the current compilation unit. Okay, so that's the overall scope. So once, let's say I have defined a particular pre-processing directive, then as long as many files as I compile, after that they will be able to see the effects of that. So let's look at few examples. These things will become more clear. Okay, we'll start off with the tick include. So the file inclusion or the tick include compile directives is used to insert the the entire content of source file in another file during the compilation. So is as good as you have a common reusable code, or you have spread it out some code in multiple files to make it easy to manage, and you want that functionality to become available in another file as a physical separation, right? So you use the tick include compiler directive, and what tick include does is it does the equivalent job of copy pasting that entire content into this file. That's what it does. It doesn't do it literally, but the effects of the tick include is as good as doing the copy paste. And the result though, the contents of the included appear in the place of tick includer compiler directives, and the compiler directive tick include can be specified anywhere, okay, within your SystemVerilog source description. Anywhere you can specify. I'm just showing one typical example. This is actually a package in which the multiple files that belong to a test bench. These are all tests that are being tick included in a top level test package, right? So then what happens is these all class definition become part of the location where they are included. So anywhere in your SystemVerilog code, you can do tick include as long as the content that brings in is legal to go in at that point, right? So that of course you need to ensure, but as long as it is legal to go in at that point, you can do the tick include. Okay, the second compiler directive that's very useful is tick define. So tick define creates a macro for text substitution, and after the text macro is defined, it can be used in the source description by using the tick character and followed by the macro name. So for example, I can say tick define this dr5 h0 and then define IER as 5 tick hex 1, and then tick define IIR as 5 hex h2 5 hex 2. So now what I can do is I can use this IER at any place. Let's say I am doing a case based decode statement, then the condition for that case decode, I can mention this value tick IER, and when I say tick IER, it gets replaced with this 5 tick h1. okay, so it just does a literal substitution, as tick include copies the entire content of that file into this file. When you use tick and the macro name, it's just equivalent to search and replace. So in a way, it just replaces with whatever value that you have defined, and that's how this whole thing works. And let's look at few more examples. So you can actually even pass the arguments to the tick define macro. So here, for example, this passing arguments to the macros is heavily used in the context of UVM. So we say tick define UVM error, and then we are passing this bunch of arguments, and then when we pass this bunch of arguments, ultimately note that this doesn't behave like a function call. Okay, this might appear like a function call, but doesn't behave like a function call. What happens is that whatever the text that we have defined over here, eventually this text gets placed, again same thing, search and replace, although it's a multi-line, it just gets placed in that particular place where you say tick UVM error, this code will appear. So just a shorthand to accomplish like you want to write that particular code over there. So it's just a shorthand, it's not a function call that you are doing. So sometimes a question might come in your mind that why shouldn't I just use the functions instead of these sort of pre-processing macros. There are always certain limitations when you use the function, and also which you can overcome with the help of the macro. So the way you need to think about it is the macro allows you to sort of generate the code, right? That is what is happening when you use the macros, and whereas when you write the function, the code that exists over there is fixed. Okay, so here you can do some level of code generation with the help of macros where you pass the arguments. That's one thing. And second thing is since there is no actual function call that takes place, these run fast. Okay, because it doesn't have to put it into the stack and all that thing, the overhead that's involved with the function call doesn't exist when you use the macros. Okay, let's look into this tick ifdef and tick endif. So this is a concept that we were already using in our 5.4 testbench files, if you had noticed. So at the top of this file, we generally used to put this if not defined inc 5.4 config then tick define inc FIFO config, and then you will see endif, and between these two we are putting in our actual SystemVerilog code. So with this, what happens is when you tick include this particular file at some particular location in some other place, like in the, let's say in the environment, you are doing the tick include of FIFO config, and let's say you were using this FIFO config at some other place as well, right? So we have used this, for example, within the FIFO transaction as well. So when you do that, what happens is sometimes if we do not have the protection, then we could end up including the same file at multiple places, and then when that gets compiled, it could result in the duplicate definition error will start coming out, right? So to prevent that, what we are doing is we are checking this. So if we are checking if not def this macro, and then we say tick define this particular macro. So at the point, let's say if I compile the FIFO transaction independently to do some small testing, it's fine. I have included the FIFO config over there, and then it executes this particular line, and then on the line 193 the tick define gets executed, and then since it was not defined anyway, this whole content will get included and it will work fine. Right now, when I do include the FIFO transaction within the environment, and let's say before including that I have also included this FIFO config, in that case what happens is first time in the FIFO config a compile the tick include statement is executed in the context of a FIFO env, which is a top level file compared to FIFO transaction. Then this line number 192, it checks if not defined inc FIFO config, that it is going to find true because this macro is not yet defined, and then line 193 executes, in which case this macro gets defined, and then the content of this class declaration gets included in that particular environment. And then when it comes to the FIFO transaction inclusion, again we do the tick include of FIFO config.sv, and it comes to this file. And as we talked about, once the tick define is seen, then all subsequent compilation, the whatever that takes place in the scope of that compilation unit, all of them will be able to see the tick define. So now in the context of when the FIFO transaction does the tick include of this FIFO config, then this if not def inc FIFO config will no longer be true. Okay, so then this file, the repeated inclusion will be prevented. So in this way, the conditional compilation compiler directive is used to include optionally lines of SystemVerilog source description during the compilation. Okay, and these directives you can put it anywhere in the source description. So here I have put it outside to show you, but it can be anywhere. Like for example, many times when you are maintaining multiple flavors of DUT configurations, and what can happen is that there can be port differences, small port differences, there might be some small signal differences. So you can use tick ifdef to manage those. Okay, at the top while you are instancing, you can use tick ifdef and say, okay, if this type of a configuration, then some additional signals get included, and then tick else, some other signals get included, and then when you are compiling your overall test bench, you define what type of DUT configurations, and depending on that it will figure out which type of additional signals to include. So you can use these ifdefs anywhere, wherever you want to conditionally include some part of the code during the compile. Okay, so this is happening at the compile, it's not at the runtime. So just at the point where you are compiling, it gets included. During runtime you cannot do any changes. And then these actually, so these macros that we are using, the tick define, what we called about, those you can also pass it during the part of the compilation. So in your when you compile a particular code through the simulator, you can say plus define plus that particular macro name, which enables, which is equivalent to you saying tick define, and then you can use that value to implement your conditional compilation, saying that I want to use DUT config 1 or config 2. So you can do that. Okay, so when the tick ifdef is encountered, the tick ifdef text macro identifier is tested to see whether it's defined as, and then if it is defined, then what it does is whatever the group of lines that you have defined, post that gets included. Otherwise it will check for tick else or tick else if, and then if the tick else if, then it might be another macro that you are checking, and the same process repeats at the end. If none of them are defined, then tick else compiler, whatever that you have defined it under the context of tick else, gets included, but it's only one of them finally gets included. So this way you will be able to conditionally include the files, and if the macros are not defined, then those group of lines of code gets ignored, as we saw it in the case of multiple file inclusion, how the second time file inclusion got ignored. We have been using the tick time scale compiler directive already in most of our examples. Without this, even we couldn't generate a clock of write frequency, right? So the tick time scale is an important compiler directive. The syntax looks something like this. We have tick time scale, time unit, bar, time precision, and then what the time unit specifies is it specifies the unit of measurement for time and the delays that we use in the simulation, and the time precision argument specifies how delay values are rounded before being used in the simulation. Okay, so the precision and then the unit, right? So the unit, whatever the time unit that we are using, the precision for that particular time unit is specified by this time precision value, and time unit is a unit of measurement for time values such as simulation time and the delay values. And then you can use $time and $real time. This we have already been using function to provide the current simulation time. And then you have another system task called $time format, where you can set up the format in which the time information should be displayed. So there are different ways. So sometimes let's say you don't want the decimal digits to be displayed, how you can do it, or if you want those decimal digits to be displayed along with the time unit, whether it is like unit meaning like whether it's NS, PS or something like that, all that also should be displayed, how you can do it. So various format specifications, you can set it up with the $time format system task, and then whenever you use the $T to print that particular value, it will be reported according to what you have set up before. So quick example, so tick time scale 1 ns bar 1 picosecond. The time scale in the design element will now follow a directive that it will always be multiple of 1 ns. So if I say hash 5 somewhere, then it will be hash 5 ns. So that's how it gets used. And then delays are rounded to real numbers with the 3 decimal places in this particular context, or to be precise, they will be 1,000th of the nanosecond, because we have set it up as the precision as the 1 picosecond. So that's how this particular tick time scale directive gets used. SystemVerilog packages are one of the like a very popular construct for deploying reusable code. Even more, like the code libraries like UVM are deployed as a package, and third-party vendor verification IPs that are bought are also deployed as the SystemVerilog packages. So as a part of this session, let's understand how this package construct works. So the scope for us to understand the package construct is that first let's understand what's the definition of a package. Ultimately, package is, as a name itself suggests, it's packaging things together, right? So what can we package, and then how do we package? So we look at that as a part of definition of package, and then once we have packaged it, how do we access the information from that particular package, right? So that is done through importing, and then there are various ways to reference the content that we have put in the package. So how do we do that? We'll look at it, and then we'll just quickly contrast tick include versus the import. So the packages are in a way they are made accessible to the like a module or to the program block through the import statement, right? So let's understand how the import is different from the tick include that we have already seen, the compiler directive that we have already seen, and then how, when the particular variables are accessed, what is the search order in which the variables are located. So we will look at that, and then when you construct the composition of packages, that is, you put like a one package imports another package, and then this final package gets imported somewhere else, then how do we ensure that what we have included, what we have imported from other packages is also accessible to the top level, right? So if at all that requirement is there, it may or may not be there, if it is there, then how do we make it accessible? So that angle we will look into it. So let's jump into the details of package construct. Okay, we'll start with the package declaration. So packages, to formally define, they provide mechanism for sharing and sharing these among these, right? So multiple of these, right? So that's what the packages are providing. So what do we share using packages is that we can define common parameters. Like this, I have defined address width, data width. So these parameters I can share with the help of the package. I can define different type of data types, like I have this user defined enum data type, type def enum, and some APB state I have declared it over here. And note that classes are data types as well. They're just the advanced data types. So I can define class within the package to share this declaration among the other consumers. So then I can define tasks and functions. So I can definitely define utility tasks and functions that are common across multiple class or multiple modules. I can define them over here and then distribute it for usage across all of them. And then I can do the assertions, the sequence and property that we want, that I want to reuse across multiple places. So note that you are not equipping the combining the property with a directive. Okay, so this is not meant for that. It's just meant to share the definitions. So somebody will consume it, right? The package itself is not a consumer. Okay, package in a way is sort of container, and then we distribute the common container to multiple consumers. Okay, so package doesn't consume anything. So that's why we don't equip the property with some directive called either assert or cover or something like that. That we won't do within the package. And there is a reason for it. We'll look at it in the next few slides. And then also you can include the cover group. So this way you can, whatever is reusable items that you have, you can put it in a package, and then you can distribute it. See, there are various levels of reuse. So something at the topmost level reuse, you put it in the package. Okay, so that's how you need to understand. Few lines of reuse, you do it through functions. Few set of functions, you reuse it through class. Then few classes that you want to reuse for a particular application. When you get to that level, then it gets like combined, right? Because ultimately what you want some sort of stimulus, you want some sort of check, and you want some sort of a coverage, right? So that's what you do in the coverage driven constraint random verification. So all of it, you put it in a package and give it to some entity which imports it and builds on the top of that. Okay, so one particular interface, let's say I have APB interface, I can build everything about APB in one package and give it to somebody, right? So I can generate stimulus, I can do checks on that particular, I can do coverage, right? So everything is packaged, and that package gets used. So when you have created a package, you can share it among multiple modules, interfaces, programs, and checkers. So programs and checkers, we have not seen it. We'll see them, what are those constructs towards in the next few slides. So that is what is the package declaration. So you use the keyword package, you give space name with a semicolon. Then within a package, you can import other packages, that is allowed. And then as we talked about these different constructs that you want to make it accessible, you can provide it within the package. You can also provide variable. For example, I have declared int error status, right? So you can provide the variable, and that variable can be used at places where it is shared. So we have now understood how to declare a package. Now let's, in the next few slides, let's understand how to use the content that we have packaged at different places. Okay, so we have looked at how to declare a package. Now let's look at how to import the contents from the package. So before accessing any of the content from the packages, first thing is they must be compiled. So unless they are compiled, you cannot access. So once you have compiled, then there are two ways that you can access the content from the package. One is you can use a scope resolution operator. So for example, in this first top left corner example, what we have is we have module test package, and we have an initial block, and within that I am displaying the error status value, and then I am assigning, this will just display whatever the value that we have initialized it in the package. Since in the package we have not initialized anything int data type, by default it will show the value of 0, and then we are saying bus package, and then we are using the scope resolution operator, and then we are saying error status, which was one of the variable that we had declared within the package, equal to some value, right? And then I am able to write to that particular variable, and then here I am reading that variable and displaying its value over here, right? So this way I can access the package that is compiled using the scope resolution operator with the name of the packages. And note that if this particular package is imported across multiple modules or at any other places, interfaces, whatever the value that we update for the variable that's present within the package will be visible to the other entities as well. It is the same. Like for example, when we instance a particular class, then what happens is the data gets allocated for that particular class instance, and when we create one more instance, one more group of like whatever the property that we have declared within the class, one more copy of that gets allocated. So if I change in this class, doesn't mean it will change in the other class unless and until that property happens to be a static type, right? So in a way you can think that the packages are never instanced. Okay, it's just the one copy of whatever that you have declared within the packages. Especially I'm talking about the variables. The other things are okay, tasks and functions are fine, but variables is just one copy. So if you change it at one place, it reflects at the other place as well. So sometimes what happens is every time you don't want to use the scope resolution operator, it becomes long and inconvenient. So if I directly want to access the error status wherever I want to access from the package, then what you can do is you can use this import statement. So this is let's look at the second example where I have module test package _1. So I'm doing import. I'm saying import bus package scope resolution operator error status. So I'm importing this variable. So when I import this, when I put this import statement after the line 150, error status becomes a part of this module itself. Okay, so now it allows the identifiers declared in the packages to be visible within the current scope. Okay, then what happens is you can access them without using the package name qualifier. So now when I come in over here, I can just say error status equal to 20. There's no problem. Okay, and then I can write it, then I can read it. As we pointed out here also, even when you do it with the import, when you update this particular value, what happens is that this value will again get reflected in all the places where the package is imported, or it is being seen through the scope resolution operator, right? Because it's a single copy, it gets seen. So when you import, what you can do is you have two options. You can selectively import the information that you intend to use like this, and then you use it, or what you can do is you can import everything. So that's generally most of the places that's how it's done. Slightly lazy way, but that's what is the most places we use it. So what we do is we say import bus package : and then we will use star. Okay, and then star means import everything that's present within that particular package. Although when you do the import, only what you use really gets imported, or what you don't use doesn't really get imported. So that's another good thing about the package. Okay, when you import packages, there is one problem that you might face. So let's look at it. So let's look at it with an example. So I have a module test package 1, and then we are importing this error status variable from our package bus package. And then on this line 51, I am also declaring another local variable within this module called error status, right? So think of it like this. So in the real life development, what can happen is that I might not have this bus package, right? So let's say we are buying that verification IP, and prior to that in my module I have already declared this bird error status because we are implementing the same specification. So I might have that error status might be a popular term. So I have already declared a variable called error status. Now what happens is eventually somebody gives us this package bus package and tells us that yeah, you can use this. So now when I say import bus package error status from that particular package, then it leads to a conflict in the module namespace, because in the module namespace I already have a variable called error status, and when I import, if I had used it with the scope resolution operator, it would still have been fine. right? But if I import, then whatever I'm importing becomes now part of the module namespace, and in the module namespace I already have the error status. So if you try to do that, then it will show you error that error status is already declared in this scope. So when that happens, you have two options. Either you can change the name of the variable wherever it is under your control, or you use it with the the scope resolution operator. Okay, so without importing, you can use the scope resolution operator to solve that particular problem. But the long-term solution is generally it's a good idea to make sure that there is no naming conflict. You choose a different name. That's always a better long-term solution. We'll look into the difference of tick include versus import. Both the package and tick include can contain something that you want to share between module, class, interface, or program. Both of them can be used. Okay, but let's understand what is the difference and why packages are suitable in certain cases than the tick include. So tick include, as we have seen, is just a shortcut to copy pasting the text in a file, and it takes place as a part of pre-processing step, okay, where the SystemVerilog syntax is not understood. So this is an important point that you might want to keep in mind. And then packages can be compiled separately. Okay, so this is another important point from the package point of view. They can be compiled separately, and also they can be turned into a binary form of libraries. Okay, so when we do the UVM, we'll see that the entire reusable UVM package is pre-compiled in the form of an binary format. The advantage of that is when you do this, the compiler can read that binary version much faster than the original source code form, because it doesn't have to do the analysis, check and all that, right? It's all those things have already been taken care, so you don't have to do that. But whereas when you do the tick include, the content again eventually after the pre-processing step, as we had seen in the compiler directive implementation, it has to go through the analysis and compilation step again, whereas that won't be applicable when you do the import. Okay, so and the other thing is that even when you import my package ::star, it doesn't mean that entire all the variables and everything, it doesn't come from that to the entity that is importing it, right? Only what actually you use becomes visible. Okay, so if you don't use it, then there is no problem. So like in the previous example, if we had done just import bus package ::star, and if the error status was never used, then there would not have been any problem. Since we were specifically trying to use the error status, or we're trying to import it, is when the conflict comes. And other thing is that when you import something from the package, it does not duplicate anything. Okay, so it's still a unique thing that remains. It remains as one entity, one variable, whereas when you do the tick include, it duplicates it in every place where you do the tick include. So that is the difference between your tick include and import. Okay, we'll understand how the search order for the variable works when we use it in the presence of package. So import, when we do the import, the compiler becomes aware that okay, package is another place where I can find something if I need to. Okay, so that is what it tells to the package. It's like a store of items or something like that. Okay, this is available in this particular cabinet, and whenever you need something, if you are not able to find, then come open this cabinet and look at it. Like it's like a storage room. In a way, you can think of it like that. So now let's understand how it works. So whenever compiler finds reference to a variable, data types, tasks, or functions, what it does is it first starts searching it in the local space. Wherever that you are referenced, let's say in a task or something, I reference one particular variable, error status, then it starts looking at within that particular task if I have locally declared that variable. If not, goes up to the module level, and so on and so forth, right? So we have looked at this type of a hierarchy before as well. And then if it is already found in the local scope, then it's the end of search. But when it's not found, then what it starts doing is it starts looking into the packages. Okay, and packages are searched after the local scope, and minimum like whenever you import the package, as we have been discussing, only minimum number of names are brought into the local like the importing namespace, and what is that minimum is whatever that is being used gets brought in, and whatever is not used it doesn't bring in, to minimize the conflicts. And it is one good thing and bad thing. It is good in, but it's mostly good thing. So when you import the enumerated type, okay, like for example in the bus package we had an enumerated type for the bus states. So when you enumerate that, when you import the package, the enumerated data type becomes available, but those named constants for the state that we have, like let's say idle, transfer, or something like that, those names for the state or the enumerated name constants, they don't become visible. They are also called as labels. They don't become visible. So those you still have to access them using the package name double colon, using the scope resolution operator only. You need to access those enumerated name constants. Now, why I'm saying that is an advantage is typically when you implement any protocol or any standard specification, people tend to use the similar type of enums. Okay, so now when you import from another vendor for some reusability, then they would have also defined the similar data type. So that enum conflict at least can be avoided. I mean, I have seen the cases where it really helps. So you have to remember that when you import enum, only the type becomes available, but those named constant within those curly braces, those won't be available. Those still have to be accessed using the scope resolution operator. Few more points. So we have already discussed that the packages cannot be instanced. Okay, so packages are not like your class or module, so they cannot be instanced. They remain as just one shared copy. Okay, one shared copy of all, and so whatever variables that you declare inside the package remain as singleton. That is, just one instance will be in the existence. So if you update it from one place, it will reflect in all the places that particular package is being used. And another point about packages are standalone. What that means is they are only dependent on themselves. In a way, you can import other packages, but that's it, right? And this is because they are just a containers. Okay, they do not consume. Like for example, module is in a way container and consumer. So it uses, so if I declare one particular task or a function within a module, then I can put an initial block and call it as well, right? But that is not how the packages work. So in a package you can't put an initial block and call whatever the tasks or functions that you have declared. So they don't have that type of an existence where the code can execute within the context of package independent of another container. So they are just like pure containers in that way. Since they do not consume anything, they just remain standalone. And so like if I had a class or something like that, or if I had instance one more module and that module contained a class, and when I had called them, I have to use, like let's say whatever, like top tb dot in some whatever internal module, and then I will call that particular task. Or within the class also we have class hierarchies. If you remember, we will say okay, this dot FIFO config dot something. So you have so any consumer has to go to that particular entity and consume it, right? So that way he has to use the hierarchical references. But since packages are standalone, they are not consuming anything. They do not have any hierarchical references to anything outside themselves. Okay, they just are containing pure containers, right? And this is why they are good for delivering third-party code, because they are not dependent, right? So if something is dependent, then even inadvertently I might try to access something from my package from somewhere else, and locally I might have kept a copy at some location in my working area, my directory structure, and it will all work in my working area. Now when I export that particular package, I might forget to export this extra thing that I had kept locally. Okay, that I might forget because that's something I was just using for testing or for some local usage that I have forgotten, but my package that I am giving it to somebody is still accessing that local code. Okay, so now when somebody uses it, it will be failing because that particular hierarchical path is non-existent in their environment, right? And then there's an unnecessary conflict saying that, hey, it works in my environment, why is it not working in yours, right? So such scenarios do not happen with the packages. That's why it's good for delivering third-party code. Those type of mistakes cannot be done. Okay, that's why UVM is deployed using the package. Packages can be imported anywhere that is legal for their content, right? So as we have talked about, like for even the tick include can be done anywhere where it is legal for their content that you are importing. But let's look at some of the places and how it affects, how it affects its visibility. So you can import a package within a module. Okay, so when you import the definition, so when like I have a module complete declaration and then I am importing a particular package, then this imported package definition will only be visible within the visible within the module. Inside the module only this will be visible. Now if I want to use, like for example, we had declared these parameters called data width for instance within the bus package. Now if I want to use that parameter for parameterizing the module itself, then what I need to do is I need to import this package definition in the module header. That is, you say just give the module name, and even you before like declaring any parameters or port, that's the module header area, so you can import a package there as well. And then if you import there, then the parameters become visible to the parameters that you intend to define for that particular module. So you can use that over there, and then you can import it at the top. Right, so generally this is the model that we use with respect to either this or this, right? So one of those two models are used. Typically use the first one to keep the visibility local to the module that is using it, but if some cases you can use this as well. So imported bus package definition will be visible to all the files that are compiled after the import statement. So here if I have multiple module definitions that get compiled, all of them will be able to see the content of the package. So typically the good practice is that you keep it restricted to who needs it, right? That's generally a good practice rather than exposing things to everyone. So we look at a scenario of export, and let's understand why we would need it. So what's happening over here is I have one data type package and then I have one top package. Inside the top package, I'm importing this particular data type package, and that data type package contains this one data type that I have defined, which is an 8-bit logic type called mask_t. Okay, so this is the broad lay of land. Let's look at let's switch the context over here a little bit, and then we'll come back to this particular export statement and why are we doing this. So I am not talking about line 90 and 93 at this point of time, don't worry about it. So we'll come back to this module top. Here what I'm doing, I'm importing this particular top package and I'm importing everything. Okay, so if I did not have line 90 and 93, let's say, okay, so if I didn't have these two lines, and if I had defined this line 106 where I want to use this mask_t mask, I am declaring a variable of the type mask_t which is present in the data type package which is imported on this line 88 within the top package, and that top package I have imported over here on the module top at line 103. Okay, so this is the scenario. Now in this case what will happen is the mask_t, it will say undefined type. Okay, that is because if you just import a package, then the content of the data type package will be visible within this top package. For example, here I am able to use data_t which belongs to this data type package. I am able to use address_t which belongs to this particular package. I could have used mask_t also. Okay, I have not used it incidentally, but I could have used it over here as well. So, but it will be visible. Okay, so whatever is this content of data type package, it will be visible within the top package, and this guy can use it. But if you want to use the content of this data type package externally through the top package, right, then you have the problem. So this guy mask_t will not be visible. So in order to solve this problem, if you want the imported packages within a package to be visible to the entity who is importing your top package, then you need to do the export of your imported package. Okay, so in a way concept makes sense, right? I have imported, I can use it, no problem. But if I want whatever I have imported to be usable to somebody externally, I need to export it. Okay, so that's the idea. So if I export it, then I can use it. So for example, after exporting, if I wanted to do this like a data_t new data. Okay, data_t is also belonging to this data type package, then there would not have been any problem. So in the earlier case, I didn't mention the problem would have been there for the data underscore t and mask underscore t both. Okay, they both would have had a problem. If I do not add this export statement, then for both this line 105 and 106, it will give me error. Instruction underscore t, no problem, because it's already available at the top package level, but the data underscore t and a mask underscore t, I would have had a problem. And when I did export, okay, what it will do is the data underscore t will not be a problem, but mask underscore t, it will still give a problem. Okay, I have added the line number 90. I have not yet added the line number 93. So it will give an error that it's an undefined data type for mask underscore t. So why this happens is, as we have seen, packages, even though I'm importing with a star, it brings in only what you use. So in this case, I'm using only data underscore t and the address underscore t from this data type package, and hence when I say export, whatever that I am using becomes visible to another guy. Okay, and what I am not using is not visible. So that is why what I now need to do, although I don't need it, but I want the, like, I means here I'm talking in the context of top package, although the top package doesn't need mask underscore t, but if somebody were to import the top package, you want the mask underscore t to be visible. So then you have to additionally explicitly import data type underscore package mask underscore t. So only when you do this, that particular the variable will be forced and become available in the namespace. When you do the star, only what you get used becomes visible in the namespace. The rest of it doesn't become visible. So only after you add line number 93 code, then your mask underscore t mask will work. Okay, so packages are sort of like, are very privacy conscious, so you need to take care of it. So we have been using class-based test benches, right? So how do packages get used in such test benches is this way. So they are used in a way hierarchically. Let's look at it. We have, like, for example, the individual verification IPs are packaged by including all relevant class files in a package. So let's say I have an APB agent. So what is an agent? You will understand when we go to UVM. So let's for now just take it that it's just a combination of your driver and monitor and some more set of classes. So I have package APB agent package, and then I'm importing UVM package over here because I am using it in the rest of the classes, and I have to do so whenever I want to use UVM. I need to use these two lines: import UVM package, scope resolution star tick include UVM macros.svh. Why do we need these two lines? We will understand briefly, but we have to do this. This is the process. And then you include all your the class files that are relevant for the APB, right? So sequence item, agent, driver, coverage monitor, then your monitor, agent, then the sequences, then read sequence, write sequence, and then your register RAL adapter. So everything related to APB is all imported over here, and then you create your APB agent package, and then you hierarchically organize it, right? So then you have the UART environment package, right? In the environment package, again you import your UVM and then you import the APB agent package. Okay, so this whatever we had created, so we imported the APB agent package, then UART agent package, modem agent package, and then the UART register package. Everything is imported in the environment package, and the environment package itself could be further imported as a test package, and so on and so forth. So you kind of hierarchically package all information. The advantage is that tomorrow I might want a APB agent somewhere else, right? So UART is not the only design who really needs the APB agent. I might need APB agent in some other design that's, let's say SPI is also using the APB. So I can now take the APB package and put it over there. So that type of a reuse, that is UART is a peer to your SPI, I2C. So that's a horizontal reuse. So the different projects are able to reuse something. That's a horizontal reuse. And there is a second reuse, that is, let's say I have built my UART environment, and then the same UART gets integrated into the SOC, and I want whatever the environment that I have built to be available at SOC level. So I can use the part of it as is. Not everything gets reused. Okay, so at SOC level, the way things are done is different compared to unit. We will look at how it is different in the future sessions, but it is different, but still part of it gets reused. So when that happens, I can just import the UART environment package, and anyway, as we know, packages allow us to really, they bring in what we use, so it's okay. So I can import everything and then subsequently use whatever I require. So that becomes part of your vertical reuse. So you can do horizontal reuse or you can do vertical reuse. Both of those scenarios you can do with the help of the packages. Okay. The reason why I mentioned that it brings in only what component is because now each of these I2C, SPI, UART, all of them have imported APB package, right? So now when you import all of these packages at the SOC level, then what can happen, right? So like, will there be a conflict? That's why I mentioned the point that since I may not use the APB package, or even if I can again separately import that particular package for my usage, because unless I use it, there is no problem, right? So that is why there is no issues even if I package it and multiple packages contain the same entity. We don't find that as a problem when we put them together again at the top. So one other pitfall that can happen that you need to take care is that if you have a class file, okay, the same class file, you should not include it in multiple packages. Like for example, what I'm saying is, let's say I have this class A, and then I have this package P and package Q, and I am doing the tick include of this a.sv in both the P as well as in the Q. Okay, this is something that you should not do. Okay, why you should not do is, when you include this common file within this two, then like I have now declared this A of A1 over here and A of A1 over here. In both of these packages, I have just declared one handle. But the data type, if I compare, right? So if I say P scope resolution operator A1 and Q scope resolution operator A1, they won't be of the same data type. They will become a different data type. So they are not equivalent data types. Although the code is same, because of the way it gets included in the package, it becomes a different data type. And then if you want to assign one among another because it's the same class, then you'll end up having the problem. So when you have this type of a thing scenario, then what you can do is you can create one common package and put all the tick include for the common files in that particular common package, and then import that common package into like both the P and Q. Okay, so that's how you can solve it if you come across that scenario. So we have this question, why UVM is packaged, right? So whenever I want to use UVM, we will use these two lines. I will say import UVM package : star, and then I'll say tick include UVM macros.svh. So I'll get two questions. Why am I packaging? I mean, although I understand after looking at the advantages of the package, I just want to make it clear. So that's why I'm asking this question. Why are we putting everything UVM as a package? Why shouldn't I just do a tick include of the UVM code? That's the first question I have. And second question I have is, why do I need to additionally tick include UVM macros? Why can't they put it within the package, and hence I just get it by default, right? So those are the two questions. So let's understand the first question. UVM package, what now these days they do is, the simulators especially, they pre-compile it, okay, and they ship it. They ship the source code as well, but they ship the binary code of the UVM. So now when you compile the your source code where you import the UVM, they tend to use the binary package, binary pre-compiled UVM package for that. And because of that, now the overall the time that it takes to compile or import all the content is very fast, right? So you can imagine the UVM is like some 70,000 lines of code with some more than 300 base classes. So all of it happens within few seconds. If we had done a tick include, then every time it has to go through the process of analyzing the source code, and that itself would have taken a very long time. Okay, so that is the reason why UVM is pre-compiled and then pre-packaged and delivered to the users. And the second thing is that, like, why do we have to tick include the UVM macros. Okay, so here what happens is that macros, like if I put a tick define within a particular package, that doesn't mean anything. Okay, ultimately the macros, whatever that, like the macros do not understand anything with respect to SystemVerilog. Okay, so they don't understand anything, because as we have seen in the overall processing chain, it's a pre-processing step. Okay, so if I use something within the package with respect to a particular macro, then it gets replaced. Okay, but you can't like provide a tick define through a package, because it doesn't understand the notion of package, right? So it has to be that is why, since it happens at the pre-processing step, and that pre-processing step doesn't understand any notion of a package, it can't include its content in a package to be delivered. So it has to be delivered separately, because these two are separate components. Like a pre-processing step is a separate component, package is a separate component. So that is why those two are they need to be delivered separately. That's why you need to import the package, and then you need to include the UVM macros. Okay, so that's why you have to do these two lines. And so I hope that makes it clear that by importing the package, you get the speed, and then you cannot include it because they belong to pre-processing step and not the compilation step, whereas the package belongs to the compilation step. So they have to be delivered separately. We'll look at some of the utility system tasks and functions. Some of them we have already used and looked at it in a different context when we were covering other sessions. The idea of this few next two slides, like total 3 slides, is to give you an exposure to the fact that these type of system tasks and functions exist, and like broadly what category of functions are present. We will not go in detail into each of the functions and tasks and as to what exactly they do, what arguments they take. We are not going to go look at those level of details. You can refer to LRM, but the as I said, the idea is that have the awareness to the category that is available, so that on the need basis you can refer them. So let's quickly start them off. So we have simulation control task category, wherein you can do, like for example, we have been using $finish and we have used $exit in error cases, and then you also have a $stop. I think in the bootstrap verification with Verilog, I think we had used all three of them. So you can use this for either suspending or terminating the simulation, and then you have tasks for like simulation, the time system functions. You have $time, $STime, $real time provides access to current simulation time in different formats. And then you have time scale system functions, wherein you can do print time scale, then it will print the time unit and the time precision. And using $time format, you can configure how these system time system functions, simulations time system functions will display the time information within the simulation log. And then you have a bunch of conversion functions. So these conversion functions are from real values to different type of signed, unsigned values and bits. So those conversion functions, when you are dealing with the real number, you can remember that you have the functions to convert between different formats. And then we have data query function. So you can actually use this $type name to find out the data type. So sometimes this is useful. $bits is useful. So like if you are iterating over an array, and let's say especially a vector, and if you want to make that generalized, instead of hard coding the size, you can say $bits of that particular vector, and it will give you the number of bits in it, and so you can iterate over it. So dollar is unbounded. I mean, helps you find out whether the the array that you are dealing with is bound or unbound type. And then you have the array query functions. So if you are generalizing the code, then if you want to know, like you receive a data type and you want to generalize it to process any number of dimensions, then you can use you can find out the dimensions of the array, and then you can actually query the different dimensions and get information about it. I've just shown one example how the numbers would show up when you query the dimension. Then you have bunch of math functions. I think even the math function includes these all trigonometric functions are also included. Whatever the math functions that are supported by C are also supported by the SystemVerilog. So for example, if you have to ever somebody asks you, hey, generate a sinusoidal wave using SystemVerilog, you can still do it. And in the waveform viewer, there is a mode to visualize a particular like a real so you have to use, of course, a real variable, right? So the result would be a real value. So those real variables, when you add in the waveform, so you have an option where you can right click and say visualize it as a waveform, okay, analog waveform. So then it will show you the actual sinusoidal type of a signal. So sometimes these are used while like doing the model of PLLs and all that, like PLLs meaning as a concept of spread spectrum that comes in eventually when you do the high speed IO protocols. To spread them, you use different functions, or some cases you use the ramp functions. So in those cases, the math libraries could be potentially useful. Not that I have really ever had an opportunity to use them. This clog2, the logarithmic function, however, is useful. Like given the total number of bits, if you want to find out how many bits it takes to represent it, stuff like that, the clog2 is still useful while doing the parameterization. And then you have the bit vector system functions. These are useful, okay? So while solving, especially while solving constraints, if I want to say that I want to randomize a particular variable such that the number of ones is some particular random number, then I can use a dollar count of ones to find out. One hot is also useful. One hot zero is also useful. So count ones, one hot zero, these are useful functions because they can be used many times in constraints or constraint related problem solving. And then we have severity control tasks. We have $fatal, $error, $warning, $info. I think we have already seen how they work, how they behave when used in the simulation. And then we have a bunch of assertion control system tasks where an assertions could be turned off or on, and then you can control how it behaves when there is a vacuous conditions. And then if you want to disable kill a particular assertion, you can use these assertion control tasks. Then we have sample value system functions. So some of them we have used already in the context of assertions. Sampled, you can print the value in the preponed region. Rows fell. So you can use this for detecting edges. Then you have the stable, which we have used, changed, I think past. I think I think these functions we have definitely used in the context of assertion. There's one miscellaneous tasks and functions called $system. So $system is also one of the, so some of, like, I would call this as a magic function. You can actually run a Linux command using this. So you can say $system move something to something. Okay, so then this, whenever this particular call gets executed, then it will execute this move command on the shell. So when you are doing some automation, then you will find the $system function to be useful. So at this point, this is the set of system tasks and functions. There is the usage information is available in the LRM. As and when you need, you can look up the individual tasks or functions. But what you need to remember is have a snapshot of this fact that these different category of functions are available, and then that you can make use when the need arises. So we'll briefly look into what is a program block. So a program block was meant to be the container for the Testbench code. Okay, so we had even used it in the context of FIFO Testbench for the completeness. So the idea was that whatever that code that you write for the purpose of Testbench, you put it in a program block, and it had almost equivalent capabilities as module. So whatever module could do, even the program block can do. And the idea was to schedule the code that you put in the program block in the reactive region of our scheduling semantics to avoid the race, right? So that is that, okay, let the DUT do its job, and then in the reactive region let the test bench respond to it. That was the whole big picture understanding. But what has been discovered eventually is that it's not that useful. Okay, that is what has been discovered. So many of the time these programming languages are created by different committees. So when things get created by a committee of people, then different concepts get pushed by different set of people, because things are coming from different languages together, right? So then people who are defining the language are coming from different background, so things get pushed. Sometimes few things become useful, and sometimes few things they don't turn out the way they were intended. So program block seems to be one of those type of a feature. So as long as you use clocking blocks and non-blocking assignments, there are no additional races that can be prevented from the program block. That's what has been concluded, and that is the reason, if you look at it, UVM doesn't use the program block. Okay, so that is what seals the fate of the program block. So for all practical purposes, program block is same as module in terms of its ability as a container, and also suffers from the same problems that a module can suffer in terms of race. Okay, so predominantly, right, at a fundamental level, there are two types of races. So one is erroneous use of the blocking assignments for the sequential logic, right? You have race within your so when you do this, we have seen several of these scenarios with the blocking assignments. So this is a race that can exist in the DUT regardless of race between the test bench and DUT. Okay, so if you do this, whether you use program block or we don't use program block, that particular race is going to exist, right? So that is one fundamental reason. And the second fundamental reason for the races is the erroneous use of the non-blocking assignments in combinational gated clock logic. So if you create a gated clock logic, so for doing the power savings, they create gated clocks, and while doing that, there are certain guidelines that needs to be followed. So when you don't do that, and then you use the non-blocking statement for in the combinational logic for the for generating the gated clock, there is again a possibility of race, not possibility, there is a race in the DUT, which will happen regardless of whether there is a race between DUT and test bench. Okay, so and whatever the race conditions, that these two fundamental race conditions that we are talking about, the practical cases I'm talking about, there are many more cases, but I'm talking about the practical cases that matter every day. These two forms of race, they exist in DUT, and if the similar type of a code is used within the program block, they exist within the program block as well. So it's not that you're sort of totally cutting away from those. So fundamental recommendation is that you rely on the clocking blocks, and even if you are not using clocking block, as long as you do the non-blocking assignments, I think it's kind of good to go. There is no further type of races that you can really prevent using the program block. About this gated clock, one fundamental concept that you need to understand over here is that there are some ways, like for example, the simulators are also designed in a way that it expects the modeling to be done in certain way to function correctly. Okay, so that is the main idea, right? So like clock is considered as something that is expected to kind of happen before anything you do in the design. Now, like when you do the gated clock and use additional combinational element in that, what happens is that fundamental rule gets violated, that now clock changes, and again in the active region, because you have used combination, again clock itself can change, leading to re-execution again. So in those type of scenarios, there are certain guidelines. I am not going to go in deep about how exactly those guidelines needs to be followed when you do the gated clock, but if you do not follow them, then what happens is that your clock itself is acting as a logic, and it's participating in that whole process of evaluation, rather than happening once and let the other logic execute. and that can again lead to the race conditions. Okay, so just remember that basically, I mean, bottom line, what is the essential point that we are trying to communicate over here is that as long as you use clocking block and non-blocking type of an assignment, there are no more races that a program block can help you prevent. That is the bottom line basic point that I want you to remember. Even if these other points that we are discussing over here are not very clear, that is the main thing that I want you to remember. So there exists this program block construct. It was designed that it will execute in reactive and hence minimize the races, but within that, whatever the races that exists in the active region, they are going to continue in the reactive region because they are two mirrors, right? If you remember from our scheduling semantics. So that way, fundamentally, it is still not race free. Okay, so unless if you violate the coding guidelines, and you can have race condition. So that is the point that you should that is the takeaway from this whole discussion. So that's why we are not going to discuss program block in any further length, but take it for like at the very basic level. Program block is same as whatever the capabilities that we had in the module. You have the same capabilities in the program block as well, and you can use that for the test bench. That is what is the definition for it. So checker block is again a new container that has been introduced in the, I think, like the 2017 LRM. Checkers are like module, again similar like to a program block. Checker is a module equivalent for holding assertions. Okay, it's mainly used in building formal verification IP. So the way we have simulation verification IPs for each of the protocol and for many other things. So similar way for the formal verification engine, there are assertion based verification IPs that are created, and those are bundled using the checker construct. Okay, so remember that we cannot use, there are some limitations and then there are some benefits of using the checker blocks if you are building a formal verification IP. So we cannot use concurrent assertions inside the class. So we needed a module that contained the reusable auxiliary code and the assertions, and we bound that particular module to a design hierarchy so that we can get access to the signals. So in the above solution, this whatever the way we have been creating this solution using a module and module containing auxiliary logic and then set of properties, and that particular module we bind it to a particular hierarchy so that without really touching that particular RTL code, we are able to instance this module in that particular hierarchy and able to access those signals, right? So the same thing, you can now replace that particular module with the checker. So instead of saying module space some name, you remove module and put the keyword checker, and it will all behave the same. Okay, so like modules, checkers also can contain cover group as well. So if you are implementing coverage, it can have the cover group as well. So the main advantage why you can use checker is, so some of the tools can recognize that it is a verification only module. So what happens when you look at the hierarchy, and like bind actually leads to that hierarchy, that actually instancing sort of, if you look in the hierarchy, you will, when you click at that particular location where you are bound, it will show up as an instance over there. Now when you are browsing that hierarchy, okay, then you might, like, sometimes you might feel confused that, oh, why is this particular module coming in over here. So in such cases, like for example, some tools recognize that, oh, instead of module, if you put it as a checker, it will give some symbol or something to tell that, oh, it's a test bench component and not a design module. And there are some additional features that are available called like free variables and procedural instantiations, which are more useful for the formal verification. So checker is in a way is a container that's, as I told, it's more useful if you are building formal verification IPs, and it's a flexible reusable verification library development component, and it's actually used in, there is one SVA checker library. So this is something that you can Google and find out more. There's a bunch of already reusable properties and sequences have been put in this SVA checker library. Whether you use it or not, you can just have a look at it to understand how the different ways the operators of the sequence and the operator of property get used, so that when you create your own assertions, you can benefit from that. So you can look it up in the web. So yeah, I think that's what is the checker block. I think when if you build the formal verification IPs, and then you can look more deeper into this construct. So there are some cases where some parts of the test bench are implemented in C. Okay, so this is not something, we are not talking about like some SOC processor executing C code. Okay, we are not talking about that. This is as a simulation engine. I am simulating both the SystemVerilog as well as C code. It's not running on some processor. Even any design that doesn't even contain processor wants to implement something in C. Okay, so I can use that C code over here. So one of the examples that I have seen is like when you do any like LDPC encoder decoders, then what happens is the sometimes the standard specifications themselves provide some reference C code to demonstrate the algorithm, right? So they provide this formal definition of algorithm, and then along with that they also provide a C code to kind of make it more clear. Okay, so in such cases, now if I implemented that encoder decoder, right, that those are your error detection and correction type of mechanism, encoding and decoding mechanism that help you do single or a multi-bit error detection. So that's LDPC is one of those algorithms used in the cellular communications and even in the various storage drives and all that. So what you can do is you can take that spec provided C algorithm, okay, and you can use that as a reference model. As we know that we all need reference model to do the checks, correct? So what we can do is we can use that C code as a reference model, and from the SystemVerilog call that reference code model, and whatever the output that it is generating, you can take that and do the comparison in your simulation. That's one of the application I'm talking about, but there could be other applications that people might be using that could be also due to legacy reasons. So some cases, some of the companies, especially the older ones, they, in the absence of like this type of a high level verification language like SystemVerilog, when they needed these capabilities of object orientation and all that, so they have built various test benches in C, C++ as well. Now what happens is they want like a part SystemVerilog, because new things come in for some new feature, they want to use SystemVerilog, but whatever that was built previously, they want to continue to use it. Those also could be potentially interfaced using this DPI. DPI is the direct programming interface. So SystemVerilog DPI is basically interface between your SystemVerilog and a foreign programming language, in particular the C language. Although Python interfacing is also growing, but whenever we talk formally in the context of DPI, we only talk about C. So it allows designer to easily call C functions from SystemVerilog and export SystemVerilog functions so that they can be called from C, both the ways, right? So a SystemVerilog can call a C function, a C function can call a function from SystemVerilog. Both the ways you can do it. Like for example, C calling SystemVerilog can help you, let's say, sample some signal values that is present in your SystemVerilog and get that to the C word to do something. Okay, so that can also be done. In the absence of DPI, traditionally the C programs were interfaced to Verilog programs using something called like a Verilog programming interface, PLI, or a Verilog procedural interface, VPI, right? PLI and VPI were used in the Verilog, and that had little bit of a lengthy procedure in terms of compiling and setting up. With the DPI, it has become much more simpler. Okay, it is definitely, it has become simpler. So let's look at how like one quick example of how this whole thing works. So we have a DPI module and some ports. So what you do is if you want to call a function from C, you say import DPI function, and then you provide the function prototype that you have in the C. Okay, so for example, whatever the prototype that I have, that exact prototype, you put it over here. Okay, so you say function void, and then of course this is in C syntax, but here you are putting it in the form of like an SystemVerilog syntax, but essentially the whole idea remains the same, right? So you match all the arguments and then the return type and everything. So and then you say import. Okay, and then once you have done this, then you can just call them directly. Okay, when we were calling the VPIs or PLIs, they kind of behaved like a system function. So we had to use dollar to call them. But for calling the DPIs, you don't need to use any dollar. Whatever the prototype that you have provided in this import, you can directly call them C from SV and pass whatever the arguments, and it will all work. So when you do this, it will really call the C function, and whatever processing that is presented over there, it will happen. It can have return values, and you can get like some arrays and stuff like that, and then use those arrays in the SystemVerilog for doing something. So this could be a reference model. You pass some information to the reference model. The reference model does processing, returns some information into the SystemVerilog world, and then you can do some check or comparisons, right? So and then that can be your scoreboard. And then if you want to call something from the C that belongs in the SystemVerilog world, then there's nothing special. So you define any of your functions, right? So SystemVerilog functions, you define it, and that function prototype, now you provide it in the C world. So there you say extern, and then provide exact whatever the prototype matching equivalently in the C. Okay, so now this gets imported from the SystemVerilog, and whenever you call this, the control will move to the simulator in the SystemVerilog domain, and it will execute that and return. So bottom line is, I think like some of these simulators that if you look at it more closely, they ultimately translate everything to a C code. Okay, so even our SystemVerilog gets converted to C code, then C gets compiled into whatever like object, and they link everything, and then when it becomes an executable, like it's like as if when you compile a C code, it becomes a.out and you execute, right? Something similar to that. I mean, I don't know all the details, but ultimately our SystemVerilog and whatever we write, it gets converted into some sort of a C object files, and then you link them. When you look at what it has littered in the work directories or the places wherever, so you can find those traces actually. Based on that, I'm guessing. So because of that, I think like interfacing C is sort of natural to this whole SystemVerilog. But yeah, from the user perspective, you can do this import of the DPI function when you want to call something that is present in the C. You want to call it in the SV, then you do the import. And if you are defined something in the SV and you want that to be called from C, then you actually have to do export. I forgot to tell this point. So you have to do export DPI function prototype you can provide, and that same prototype you will have to declare it within the context of C using the extern. And when you do this, you actually here you don't communicate whatever the arguments that you are passing. You just say this function, and then here you can reflect the arguments within the C, and you can call them. So this concludes the the sort of like brief idea into how the DPIs work. We are not going to go very detailed into it. It's a specialized area. There are few things. Basically, the main thing with respect to DPIs is how do you convert various SystemVerilog data types to C data types, and from C data types to SystemVerilog. That is the main core problem that you will face when you explore DPIs further. And then like the of course those compiler flag settings and all that, those setup related things you will face when you deal with the DPIs. But just remember that when you have that problem, remember that the DPI solution exists. It's not that every test bench is really going to use the DPIs. Few specialized test benches will end up using it, and when they do, you can explore further and get to know more about it. This concludes the session on SystemVerilog preprocessing and packaging. So we looked at how different preprocessing compiler directives help us achieve different type of code reuse, like tick include, how you can do the tick include to write code in different files and still put them together, and then tick ifdef for the conditional inclusion of the code. So sometimes, let's say you had a DUT, two different types of DUTs. like one with, let's say, a certain set of features and another DUT with a different set of features, slightly different set of features and slightly different ports, then you cannot dynamically switch between the different types of DUTs. For that, you have to use the ifdef to conditionally compile only one of them. Okay, so that is one of the other use case for the tick ifdef. We had looked at how it can be used for the multiple file protection. We looked at packages, how packages are useful for building the verification IPs or for sharing the reusable test bench code, and why UVM has been packaged, and then what's the difference between our import and include. That's an important concept. And then we briefly looked at program block, and we understood that ultimately that construct has not met its objective, and we looked at the checker, which is useful in the formal verification. And then we also looked at the DPI, which is useful for interfacing your SystemVerilog code to the C functions. And we looked at bunch of system tasks and functions. Some of them we have already used. The ones that we have used are important ones that find application in everyday life. The rest of them categorically we have quickly had a quick scan at it, so you can remember them, and as and when if you have some requirement in that particular area, then you can revisit the LRM and get to know more about that particular task or function for your usage. So this concludes this session, and thank you for listening.